Okay, 10 after 9. Time for today's first lecture. Now, previously, well, last week, 7 days ago, we talked about, sorry for this Chinese, okay? I believe in the remaining part of this PowerPoint slide, I has already changed everything into English, okay? There are 4 different kinds of specifications when it comes to control system design: stability, accuracy, speed, and the final specification, which is relatively unfamiliar for the probably most of us, is robustness. Okay. Now, what do I mean? I have a robust character. It can be reflect from the fact that I'm not skimmed, which means I understand that there will always be haters on the internet. And in my humble opinion, I think those haters, the only thing they can care about is they themselves. So if they don't care about me, why should I care about what they have to say, right? So if I'm not sensitive to those statements, then I probably has a more robust personality or more robust characters. Same thing happen to control systems. There will always be haters on the internet. And similarly, there will always be uncertainties in the use of control systems, in the application of control systems. When you operate a control system, uncertainties are most certainly inevitable, okay? Now, so as a result, closed-loop control should produce the desired output under the influence of various uncertainties, which include input disturbance, parameter variation, as well as measurement noise. So please keep in mind, there are 3 different types of uncertainties: parameter variation, input disturbances, and measurement noise. All right, now let's focus for the time being on robustness. Control system robustness is, of course, a crucial measure of how well our control system or controller will perform when faced with the inevitable difference. The key word here is inevitable, which means they will always be there, okay? Inevitable differences between your theoretical plan model and the actual physical hardware. So our theoretical plan model, at the end of the day, is, after all, a theoretical model. So it has been idealized for the purpose of simplicity. Okay, so there are always some discrepancies between the actual system and the mathematical model that are used to describe the process or the object being controlled. Okay, so therefore, my mathematical models are always an approximation. This statement is very, very true. They cannot perfectly capture every detail of real system. These discrepancies, known as model uncertainty, arise from variation of physical parameters, such as mass changing as a rocket burns fuel. So the mass of the rocket always become smaller or smaller, right? And our model dynamics, such as friction and sensor delay. Friction, trust me, is a very, very complex phenomenon. It's extremely difficult to accurately model friction, all right? So therefore, highly precise position control is always a challenge. And the very reason for that is the existence of friction. and external disturbances. So the goal of robust design, therefore, is to create a controller that is not brittle, which means it should work reliably, not just in a perfect simulation, but on actual hardware in the unpredictable real world. There are many uncertainties that we cannot foresee, all right? So, like it or not, we'll encounter them. And like it or not, we have to deal with them, okay? And that is the very issue robustness want to address. Now, let me give you an example, which is a control system exists in every one of us. That is the cerebral autoregulation control system. Now, it refers to the ability of the cerebral vascular system to regulate the blood flow in response to change in blood pressure. So here, on the horizontal axis, the independent variable is blood pressure of our body. As you probably already understand, our blood pressure is not always a constant. Actually, it changes all the time. However, the cerebral blood flow, which is the blood flow in our brain, has to be a constant because we have to provide constant blood pressure to the brain in order for the brain to function properly. All right? But if blood pressures change, that will create disturbance to our brain cerebral blood flow control system. So we need our cerebral blood flow control system need to deal with that kind of uncertainty, that kinds of variations, okay? My blood pressure can go higher and can go lower, but within a with a reasonable range, the blood flow inside my brain should be as constant, as steady as possible. Of course, under extreme condition, okay, my brain blood flow control system can no longer regulate the blood flow, but that happens only under extreme conditions, all right? So, however, for a person with normal blood pressure and a person with chronic hypertension problem, you will see that this so-called stable cerebral autoregulation range of the blood pressure shifted, right? Originally, it's in this region. If my blood pressure is higher than normal, higher than healthy persons, it will probably shift it to this interval, okay? Why is this happen? Because my blood pressure is typically higher. So my cerebral blood flow control system somehow has to adapt to this unfavorable condition, all right? So that is how powerful our brain or our body is, okay? But there is always a limit. For example, the first thing is, how do I know how much blood flow I have? Or you can use a sensor such as this, which we call transcranial Doppler or simply DCD. That is what that device look like. Now, for people suffers acute stroke, you will see that this curve, the shape of this curve, altered entirely, all right? Now, in this particular situation, such a person, of course, is very ill. His brain has probably been damaged. Now, and as a result, its cerebral regulation, autoregulation function has been compromised. So as the blood pressure go higher, its blood flow also go higher. Okay, so there is a proportional trend, positive correlation between these two variables. That is not good because our brain requires steady blood flow supply in order for our brains to function properly. So this is another example of our biofeedback control system. The reason why I want to emphasize is that I want you to have an idea that control systems are not just exist in an area of engineering, in particular mechanical and electric engineering. It actually happens in many different aspects of our life, okay, of our world, okay? Now, let's switch our gear. The next topic is I want to tell you about the stages of control system development. Now, I already make my mind. I want to develop a control system. So what is a proper step-by-step procedure to help me do that, okay? I divide the process of control system development into four stages. The first stage is specify your goal. What do you want? Okay. The problem with teenagers, I'm not laugh at them. I'm not look down on them. Okay. I think sometimes the difficulty encountered by teenagers is they don't know what they want with themselves. Okay. They don't have a clear goal for their life. Okay. So the first thing we need to do to develop a control system is specify our goal. This is not necessarily easy. Okay. Now, and the second thing is we need to determine the output to go with our goal. Okay. Now, so choosing the right output variable is essential for achieving the desired control goal because it determines what the system is trying to regulate or maintain. Okay, if I don't choose the right output variable, I can mess up with my control goal. Okay, so if the wrong output is chosen, then the controller may focus on an irrelevant or less important aspect of the system, and as a result, leading to poor performance or instability. All right. Now, an example is temperature control. Now, what is the goal of our air conditioner? It's not air control. It's not temperature control. It's for thermal comfort. Why? During the cold winter, I want the room to be warm. During the summer, I want the room to be cool, cold, comfortable. So the goal here is thermal comfort. Okay. Now, for this very goal, what output variable do we choose? At least for the time being, temperature. But does temperature equal to thermal comfort? Of course not. Why? Because thermal comfort depends on many things. For example, even before my birth in 1955, these two scholars has already proposed a heat stress index, okay, which has everything to do with thermal comfort. All right, heat stress index was introduced to quantify thermal comfort, and such an index has been widely accepted. Okay, now, so what are the components of heat stress index? Of course, it has something to do with temperature. But it also is related to our metabolic rate. If you are a very fit person, by contrast, I'm a big guy. My BMI well, I'm overweight, very seriously overweight. So metabolic rate are entirely different. So our tolerance to thermal variation are also very, very different. Okay. Now, it also has something to do with air velocity, right? It also has something to do with vapor pressure. And sometimes people also think it has something to do with humidity. So if you want a real thermal control comfort, those factors, actually, it also has something to do with your clothing, right? How much clothes I wear has everything to do with thermal comfort, okay? Now, so for true thermal comfort control system, I need to consider all these variables. But that is not the case in today's air conditioning industry. All we care about is temperature control. Why is that the case? Okay, why is that the case? Okay, so apparently there are a lot of things we can improve when it comes to thermal comfort. Now, another example, vibration comfort. The goal here is when I'm inside a vehicle, when the car is moving, okay, I want to sit inside and feel comfortable. I hate vibrations, okay? Now, it can even make me dizzy, all right? So, when it comes to the framework of closed-loop feedback controls, let's identify the 4 major components for this condition, okay? The process, of course, is the vehicle that we are driving, okay? And the actuator is the suspension system. And we need to have a controller to, if possible, to adaptively and dynamically change the operation of the suspension system, okay? We saw that before, magic body control, remember? Okay, and we need to have a sensor, all right? But now comes the problem. If vibration comfort is the control for the design of suspension system, what is the output variable? What quantifies vibration comfort? Is it displacement? Is it velocity? Is it acceleration? Or is it the derivative of acceleration, which is the jerk, which is what we call jerk, okay? Or is it the combination of all of them? Okay, so different companies have different idea about the output variable for vibration comfort. That is the very reason why when you riding a Toyota or riding a BMW car, you will see that the type of vibration that you feel are not the same, okay? For Toyota, I would say the feeling is much more, it wants you to feel comfortable. It wants you to feel smaller vibration. It wants you to feel easy. But for BMW, I think the philosophy of BMW is that it wants to give you a sense of driving, a sense that your body and the car is actually not 2 parts, but 1 part, okay? So you can get the fulfillment of car and body integration, okay? So for some of us, that may represent a kind of driving form, okay? So apparently they have different philosophy when it comes to vibration comfort. Therefore, they choose different output variable. What I'm trying to say is that choosing output variable is not easy, okay? Sometimes it's not even very, not very obvious. It would take a lot of time for us to figure out what is the optimal output variable for our control goal. All right, it's not that straightforward in many circumstances. Okay. Now the third stage for control system development is system modeling. All right. Now let's go back to the goal of control. What is control? What does control want? Control is the process of causing the output of system to conform to some desired value via adjusting the input of the system. Okay, remember, when it comes to control, the output is known. The process or the set object to be controlled should be known. The unknown to be determined is the input. So the necessary condition for control is that I need to have a model for this process. All right. So before developing a controller, we should have sufficient understanding of the system. Otherwise, if we don't know if we don't understand the system, when I apply an input to the system, what it will respond, how it will respond, I will have no idea. When I have no idea about how the system will respond to a certain input, how do I control that system? Okay, so let me give you an example. I think robotics will be the future. Okay, and I think robotics will means mechanical engineering will become more and more important because robotics, after all, is made of mechanical components such as linkage, such as gears, such as bearings, right? Okay, I'm not laughing at the people from computer science or electrical engineering, but during their college educations, they never take any course about kinematics or dynamics or mechanical materials. They never take any course has anything to do with mechanism, which is the very, very center of robotics. Okay, so if the robotics, okay, the age of robotics is coming. I think that golden age of mechanical engineering is also coming. Okay, now this is a very simple two-linkage robot model. Okay, now you have 2 degrees of freedom. The first gradient is the first joint, and Q1 represent the angular displacement of that joint. And similarly, Q2 denotes the angular displacement of the second joints. Okay, geometric parameters and kinematic parameters has also all been specified. For example, this is the location of the mass center of the first linkage, and the mass of the first linkage is M1. Now, by using Newton mechanics, by using what you have learned from the course of dynamics, you can set up a ordinary differential equations to represent this two-linked robot model. Okay, and tau 1 and tau 2 here represent the torque applied in joint 1 and joint 2 respectively. All right, so if I apply tau 1, for example, sine t, if I specify tau 2 as cosine t, what will happen to the robot? I can predict the movement of the robot by solving these 2 second-order differential equations. Right? Okay, so with such an understanding, I have a very good starting point for designing a controller for such a robot. Because whatever movement I want this robot to make, I know how to determine its input. How do I do that? From these two equations, which are the mathematical model of this robot. Now, this is, of course, a very simplified model for a very simple robot because it only has 2 degrees of freedom. For most of the industry robots, they at least have 6 degrees of freedom. Now, for humanoid robot, okay, it will have a tons of degree of freedoms, 30, 50, because it will have many, many joints. And every joint can have more than 1 degree of freedom. Look at your hands. Look at every finger of them, how many joints your hand has, okay? So, multi-degree freedom system. And you need to have a mathematical model for the entire robot body, every part of them, okay? If without those models, without those mathematical relationships to describe the input and output, what are the inputs here? Of course, joint torques. What are the output? Of course, the joint displacements, right? All the parameters in this mathematical model are given as follows, okay? Let me show you again. Where does this model come from? Newton mechanics. Newton mechanics, okay? Does people from computer science or electrical engineering take any course, at least advanced course on Newton mechanics? No, but we do. Okay, so we have some ages here in the coming age of robotics. Don't ever forget that. All right. Now, as I already mentioned that in the previous week, there are different ways to set up the mathematical model for our system. One is by using physical law. The other is system identification techniques. Now, system identification is the process of developing a mathematical model of system based on observed input and output data. Sometimes the system is simply too complex, okay? Now, I don't know how to model it, okay? So what I want to do is I want to experimentally determine the mathematical model for this system. Now, in other words, it involves applying known signal to the input system and measuring how the system responds, and then using such information to determine the relationship between the input and output. So in this case, one thing is absolutely necessary. That is, you have to apply the right input so that the dynamics of the system can be fully revealed from the excitation of your input. And you can measure the characteristic of this dynamic characteristic of that system from the output. So you have to choose the right inputs, okay? Sometimes it's not just one input, it's many different combinations of inputs, inputs of different amplitude, inputs of different frequencies, okay? Input of different types, for example, step function, impulse function, sinusoidal functions, okay? There is a huge mathematical framework to tell you how to perform system identifications, okay? So that is something, of course, we can learn in the future. But the point here is that it's a very good technique because for systems, we don't know how to model it theoretically. We can, by using system identification technique, we can always try to determine its mathematical models by real experiments, okay? Now, there is a new term arise in the past few years, and it has something to do with system modeling. The term comes from the AI industry, and this means digital twins. It means that, let's say this is a turbine, okay? It means that this is a turbine in the real world. It means that in the virtual world, by using artificial techniques, I can create its digital twin. And another turbine which perform exactly like the real world turbine, but it exists in the virtual world, okay? Exists in a computer, okay? Okay, what I want to do here, want to tell you here is that this is a new concept. This is the first thing I want you to know. The second thing I want you to know is that it is only a concept, okay? It's far from reality. I don't think a real digital twin for real physical systems can be successfully developed in, let's say, in a decade or 2 decades, okay? It's still far, far, far from becoming a reality, okay? All right. Now, the final stage of control system development is about the development of control law, all right? For example, let me give you a very simple example of a control law, which is a very popular, a very well-known control method, and we call it PID controller, all right? Now, this is a block diagram of a very straightforward feedback system. This is a set point. Now, in this case, set point represents the desired output. And sometimes we call it the ideal output. And here we have the real output. So sometimes this real output is called the actual output. I'm sorry. So this actual output represents reality. This design output represent ideal conditions. There is constantly a difference between my ideal condition and the actual condition, right? So in order to elevate the performance of the system, what we do is we determine the output error. How do we do that? Okay, we subtract the actual output from the design output, and therefore we generate an output error. And based on that output error, our controller will generate an output to the process being controlled. Okay, now the big question here is, if controller is a system itself, and you already know it is output driven, output are arrow driven or arrow driven, all right? So arrow is its input, then what should be its output? So that the overall feedback control system can perform the way we want it to perform. Now, PID says that based on its output, okay, I will generate my own output, controller output, okay? And my controller output consists of 3 different components. The first component is what we call proportional control, or simply P control. The proportional control is that my output, the output of proportional controller is that its output is directly proportional to the output arrow of this feedback control system. So the larger the output arrow of this feedback control system is, the larger the output. The larger the output of this proportional controller. Okay, so here, the output here, the output of this controller is proportional to the output arrow of this feedback control system. Now, the second component is what we call D control. Now, for D controller, the output is proportional not to the output arrow, but proportional to the rate of change of the output arrow. That is the derivative of the output arrow. Because for the same amount of output arrow, if the output arrow is increasing, then the problem is probably more, the output error is probably more challenging or more difficult to regulate, to make it smaller. By contrast, for the same amount of output error, if the output error is actually decreasing, then this amount of output error is probably no big deal because it is decreasing, and I probably expect it will come down by itself, all right? And the other thing is the third component is what we call I control or integral control. The output of the integral controller is the integral of the output error of this feedback control system. Okay, remember, okay, here you heard outputs all the time, okay? Output of the entire feedback control system. And the controller itself has an output. And the output of this PID controller actually is the sum of the output of P control, output of I control, and output of D control, all right? Now, for I control, what we have is the output error, the output of I control is proportional to the integral of the output error, okay? Now, when it comes to integral, you need to have lower band and upper band, right? What is zero? Zero represents the very time instant we start to operate the control system. We turn on the control system, all right? What is T? T means right this moment, this very time instance, all right? Okay, so this is a very simple example of control law, okay? Whenever we have a feedback control system, we need to come up with a control law, rule of control, all right? And PID control is just one example. It's definitely not the total solution. It's just an example, all right? Now, here I also want to emphasize sometimes in addition to feedback control, feed-forward control is also very helpful, okay? Keep that in mind. Now, here I want to tell you about specific control methods. When developing a control system, we basically have two fundamental approaches. The first is we tackle the controller design problem by using time domain approach. That is based on the waveform of the output variables, how it changes over time. And then we design, based on those information, we design our control methods, okay? And this method is intuitive, directly shows the system speed and error, because you can instantly or directly see how the output of the system changes with time. How fast it is, okay? How much the error it is. Is there any overshoot, undershoot? How bad is the oscillation? How unstable the system is? The time domain waveform of the output variable provides you a direct picture, okay, of what is going on. However, a second approach, and probably a more powerful approach, is frequency domain methods. And when using frequency domain methods, we actually observe system performance when facing input variables of different frequencies. Okay, that is typically when we talk about input variable of different frequency, typically it means sinusoidal input with different frequencies. All right. Now, and by using this approach, we have a easiest way to see the system relative stability. Okay, And we can also use frequency domain methods to characterize the robustness, to quantify the speed of response of the system. It provides many useful information, okay? Now, information from time and frequency domains must be cross-referenced with each other, okay? So I strongly advise you to get yourself familiar with frequency domain methods, because in your previous education of mechanical engineering, most of the courses use time domain methods to tackle their problems, okay? But if you go to electrical engineering, I think from day one, every course, every electrical engineering course tackle problems by using time domain and frequency domain methods at the same time, okay? So frequency domain methods is very important. It's just as important as time domain methods. So please, everyone, put in hard work on frequency domain aspects, okay? In this course, I will talk about frequency domain methods extensively, okay? Please pay special attention to those approaches. Okay, now, what is the goals of this course? Okay, now, actually, the core objectives of this course includes first, system analysis. Okay, now, what is system analysis? Like we introduced in last week's course, when it comes to system analysis, we assume the system is known and the input is also given. And the question here is with system and input known and given, how do I determine the output? And that is what engineering mathematics want to tell us, right? In the course of engineering mathematics, system is represented by what? By ordinary differential equations. And what's the input? Input is what I call the right-hand side of the differential equation, which is the forcing function of the differential equation. And what is output? By solving differential equations, the solution of the differential equation is the output. So the entire process of learning how to solve differential equation is actually help us to learn the tool to perform system analysis, okay? So for the course of engineering mathematics, it's probably solving differential equations is probably just a very theoretical mathematical process. There is no physics, just math. But in this course, differential equation represents system. Input represents whatever I apply to this physical system. And the output, of course, represents the response of that system, all right? Whether it's a thermal system, fluid system, electronic devices, or systems made of mechanical components, they are systems. Okay, the second objective of this course is I want to show you how to manage uncertainties, all right? Because uncertainty always there, okay? They are inevitable, okay? The very reason why we need feedback control is the existence of different kinds of uncertainties. Now, the third goal here is I want to have an overall and integrated concept of time and frequency domains. Remember, there are different approaches, but their results can be correlated. If you know what happened in time domain, you should also know at the same time what will happen in the frequency domain. If you see a phenomenon in the frequency domain, you should also understand that kind of phenomenon, when it translates to the time domain, represent what kind of impacts. All right? Now, we'll talk about this later, okay? Now, so the integrate understanding of time and frequency domain is very important. And when it comes to frequency domain, we will review Laplace transform. And with Laplace transform as the foundation, we'll then introduce you to Fourier transforms. Okay. Now, I'm sorry. What did I do? Okay. Okay. Let me emphasize one thing, okay? Don't be intimidated by the math. Let me show you, math will not be a problem, okay? The mathematics in this course will not be abstract, will not be complex, okay? It will be very straightforward. But there is one thing you need to do, is that you have to pay attention. Follow me step by step, okay? Trust me, they are not difficult at all, because mathematical approaches in this course, at least, is very systematic, okay? We can learn it by a step-by-step approach, okay? Now, okay, so don't be intimidated by the math, okay? It will not be a problem as long as you promise yourself, I will follow the math, okay, with my full attention, all right? Now, again, let me emphasize, I want you to remember this block diagram, all right, which consists of 4 components. And each of these 4 components represent a subsystem, because each of those components has its own input and output. Now, let's say if I'm you, okay, and I need to go to a doctor, all right? What is the feedback control system configuration here? The process is, of course, me, the patient, okay? And the controller is, of course, the doctor, all right? What the doctor need to do is, it need to use some medical devices to evaluate my health condition, okay? And this represents the medical devices, such as CT scan, MRI, ultrasound, or blood test, whatever. And it will compare my test result with the ideal result. And if there is an error, let's say my blood pressure is simply too high, let's say my glucose is unacceptable, then the actuator will be the treatment. The controller, which is the doctor here, will need to select a suitable, appropriate treatment to me. And this should be a closed loop system, which means it should not be an open loop process. When you apply the treatment, the doctor needs to monitor the progress of my disease. If that treatment doesn't work, then the doctor needs to adjust or reselect his treatment methods, right? Okay. Again, I want to emphasize feedback control exists in many places, okay? And when using open loop control, under many circumstances, we must stop the problem, okay? Let's talk about dementia. Why? Because it is a serious challenge for humanity. It is already the 7th leading cause of death globally. Who said that? World Health Organization. All right? Now, but for high-income countries, Taiwan is a high-income country, according, again, to WHO, not me. Alzheimer's disease and other types of dementia, okay? There are many different types of dementia. Alzheimer's is one of them, okay? Okay, let's take a 10 minutes break. 谢谢。